So, where are we? We've now computed, in principle, the table of U's. We computed the table of F's. These represent probabilities of success runs terminating for the first time or at subsequent times at trial n. What next? Well, of course, we're interested in the probability of a success run on or before trial n. In other words, we want to compute Sn. But Sn is determined completely by our slogan, by the values of the first success run probabilities, the F's. And therefore, since we know the F's, we in principle know the S's. Let's start. Well, we have the initial conditions, the boundary conditions, S1, S2, S3, and S4 are all 0. What about if n is equal to 5? Well, then S5 is a sum of F1 through F5, but F1 through F4 contribute nothing, and therefore we simply get F5 or 2 to the power minus 5. S6 gives you the sum of F's, F1 through F6. The only contributions are from F5 and F6, and that gives us 3 times 2 to the power minus 6. One more for sanity, S7 is the sum of F1 through F7. The only contributions are from F5, F6, and F7. Put it all together and we get 1 in 16. Interesting. The probabilities are increasing, and perhaps even unexpectedly fast. Let's see what the numbers come out to be. Right? So just imagine plugging it into a computer and just generating one value after the other. Here are the first 20 values for Sn. S1 through S4 are 0. S5 is 1 in 32. S7 is 1 in 16. And then we have a bunch of fractions. Right? Of course, the fractions are not edifying, so let's promptly look at them again in a decimal format. And this time, let's look at a table of S values where n ranges from multiples of 10. 10, 20, 30, 40, 50, 60, 70, 80, 90, and 100. And here are the probabilities for each of those values of n of observing a success run of length 5 at or before that value of n. So S10 is about 11%. It is actually not unlikely at all that even in 10 tosses, you'll get some run of length 5. It'll happen 1 in 10 times approximately. S20 is already about 25%. This is getting serious. This is not at all unexpected. If somebody says they tossed a coin 20 times, and somewhere in that sequence they found a success run of length 5, the chance of this is almost 1 in 4. S30, the chances are better than 1 in 3. S40, the chances are almost 1 in 2. And S100, the chances are about 80%. Of course, this is what we'd alluded to in our first tableau, in our introductory tableau. We are talking about the amazing and non-intuitive aspects of fluctuations. The chance of a success run of a given length, in this case 5, is not at all trivial. At S100, we have a resplendent 80% or slightly more than 80% chance of, in 100 tosses, finding a success run of length 5 or more in between. If you think back to those sequences, one random, one artificial, you realize where the source of the confusion was in our intuition. Immediately, we have a slogan. And to put it succinctly, it is not at all unlikely to see a success run of length 5 in even a moderately small sequence of coin tosses. This already begins to answer the fundamental question we raised about a basketball player and 2 opposing hypotheses. But before we come to it, it'll be wise to step back. We've worked very hard on this one. Take a look at the framework as a whole and see whether we can discern patterns, extensions, generalizations. After all, we worked really hard on this. We should get some value for it, some fruit for this, other than just that we've solved one problem. Before we come back and take a look at the issue of the hot hand,